Second to last lecture here. So this lecture is looking at climate and how geologists know that the climate was different in the past throughout all of Earth's history. So we'll talk about some mechanisms and some ways that geologists measure that, and then look at a couple of reasons or explanations for why climate changed in the past. So we're just going to get right into it here. We're going to talk about a list of records of climate change that humans used to determine what the climate was like in the past. So one is weather records. So if we have instruments such as thermometers that are continuously measuring temperature all around the globe, we really only have detailed weather records, including temperature and precipitation globally for the last 150 years. So it started around 1880 and then up to the present day. So if we look at data from 1880 up to the present day, though, in terms of looking at what even just weather instruments show us, is that in the last 130 years, we've had an increase of 1.4 degrees Fahrenheit globally average. Satellite data from the last 40 years also shows a similar trend in terms of looking at surface temperature on Earth. The surface temperature has also increased by about the same amount, and that's our graph here on the bottom. So a second way that we know that or have records of climate being different in the past is through cultural records. So climate influence when past civilizations could flourish, and as a couple examples, Greenland was settled in 1985, not 1985, in 985. And part of the reason why people think that Greenland was settled in 985 was that there was a warming period. So there was less ice present on Greenland, which is covered in ice now, and that's what let people settle in Greenland back then. So if Greenland was settled, that illustrates that there was a warm period from the year basically 985 or 1000 of the Common Era to about 1450. And then if we look at cultural records of paintings and things like that, so this painting on the right side was from 1565. So it was showing that it was common for rivers to freeze in Europe in this particular painting. So we know that there was a little ice age based on painting and other records from 1450 to 1850. So since 1850, though, records show that we have a warming period, and it's warmer now at any time, more so than any time it was in the last 1,000 years. If we want to look at short-term cycles of climate change, so if we kind of work our way back a little bit in terms of trying to look at more of a longer term relative to weather records and cultural records, we can use trees. So tree rings tell us the age of the tree and also the climate. This is called dendrochronology, so studying tree rings to determine past climate. And how a tree works is basically it starts growing from the center outward, and each year that a tree grows, it adds one ring outward and outward and outward. So what's cool about tree rings is you can count the number of rings, and that tells you how old the tree is if it adds one ring every year. The other cool thing about tree rings is that the thicker they are, the wetter it was that year because the tree grew better because it had adequate supply of water. And the thinner that it is for a particular ring, then that corresponds to a dry season because the tree couldn't grow as well because it didn't have enough water. Tree rings also are the combination. So if we're looking closely at one ring, a ring is a combination of light and dark. So typically the lighter color is spring and summer growth when a tree is putting on most of its growth for the year. And then when a tree goes dormant, it still grows a tiny bit, but it'll put on this kind of dark coloration. So the combination of a dark plus light, that's 1 year of growth in a tree. So if you cut down enough trees or you get enough samples, you can kind of play a detective and put a bunch of tree rings together. So you can look at the thicknesses from different trees, match up those rings, and then get a record that goes pretty far back in terms of using tree rings. So this is an example of a northern Wyoming rainfall record from the year 1300 up to the year 2000 of the Common Era using tree rings. And it has shown that in Wyoming, there's been periods of drought for quite some time in history. So the redder colors indicate drought and the bluer colors indicate a wetter condition. All right, if we look at lake sediments. These are called varves, V-A-R-V-E-S, varves as well. But lake mud or lake sediments are also a record of climate change. So each year in a lake, there will be one layer that is added to the bottom of the lake as sediment and mud kind of settles down to the bottom. And if we look, if you basically dried up a lake and then kind of cut into the material or the mud, what you would see was a bunch of layers. They're also kind of light and dark layers. The combination of light and dark is 1 year. So we have a record here of many, many years of data in this lake. So youngest is usually at the top, oldest is at the bottom, and some lakes we can go back 20,000 years of history just by looking at the mud in the lake itself. The other thing I want to point out about lake sediments is that the light and dark coloration, so light coloration typically comes from winter, where that's a wind-blown dust and material that gets into the lake during the winter and sinks to the bottom. And then the darker material is typically associated with summer and fall. When you have organisms or plants living in the lake, they die and sink to the bottom. That's what gives you the darker colors. And then a thinner layer of a lake deposit corresponds to a wetter year, and a thicker layer corresponds to a more dry year. And the reason why a thicker layer corresponds to a more dry year is that when it's dry, wind picks up dust very easily, and if you get a lot of dust going into a lake, it's going to have a thicker layer during that dry year or that drought year. We can also look at ice cores and ice layers. So we can go to a place like Greenland. So this is from the Greenland Ice Sheet Project Ice Core. And you can basically drill a hole down into a glacier and then collect the ice and analyze the ice for its age and a bunch of other factors that help us determine the past climate. So there's one example of an ice core that has been taken, and it goes all the way back to 90,400 years ago. So we have a 90,400 year record of climate and the temperature and precipitation conditions at specific points in time in history. So similar to the other two that we just talked about, ice cores, they have layers, and each layer corresponds to 1 year of history. They are also light and dark, so they'll have light and dark coloration, with the lighter layers correspond to summer, and then the darker layers correspond to winter. All right, so questions 7 and 8. So when using tree rings to examine past climates, thinner rings correspond to what kind of year, and darker bands within each year represents growth in what season. So you'll have to fill in the blank. And then question 8, so when evaluating an ice core for climate records, the light part of each layer represents which season, and the dark part represents which season. So feel free to pause. For looking at a longer term, and what I mean by longer term is looking at millions of years now at this point, longer term trends are going to be using isotopes. So if you don't know what an isotope is, it's basically that there are stable forms of every element on the periodic table, but certain elements might have what's called an isotope, which means that it has more neutrons than normal. So an oxygen isotope, oxygen can be found in oxygen 16, which is the normal oxygen that we find on the periodic table. But oxygen can also be found as what's called the O18 isotope. And the reason it's O18 is because it has 2 more neutrons, which are shown in this diagram here. So it's a little bit heavier in terms of its atomic mass or atomic weight. So why we care about these isotopes is that they act like an ancient thermometer. So in water or in rock or mud, you can test for isotopes, and if you see that there's more oxygen 16 in it, what that tells you is that the climate tended to be warmer at that point in time, because this is lighter in weight, so that means it evaporates away. And to get evaporation, it has to be pretty warm out. So evaporation from the ocean is corresponding with a higher prevalence of oxygen 16 in the environment. If it's colder, then you're going to have more heavier oxygen in it, in water, in rocks, in organisms, and you're going to find more oxygen 18. So where can we record this? So you can find it in water, you can find it in rock, but if we want to be more specific, there's these little fossils that live on the ocean floor. They're called microfossils, meaning you need a microscope to see them. They're called forams. This is what they look like. But basically, you can grind up those fossils, test for the isotopes in it, and they will tell you what the temperature and moisture conditions were like at a specific time in the past. So we look at the ratio of the heavy 18 to the light 16 to tell us about past climates. If the ratio, here's your takeaway from all this, but if the ratio is small, that corresponds to warmer periods of Earth's history because it's warm enough to evaporate the light one up into the atmosphere. So Earth would look more like this situation in a non-glacial glacier period. On the right side, if you have a large ratio, it tends to be associated with cold periods, and then your lighter oxygen 16 tends to get trapped in glaciers, and you're left behind with more of the heavy oxygen. So if you have a large ratio, then that typically corresponds to more ice on Earth. So you're ready for your next two questions. So based on this graph here, so we have our oxygen 16 to oxygen 18 ratio, or 18 to 16 ratio. And then we have time. This is millions of years ago. So we have 1 million, 2 million, 3 million, 4 million years ago. So question 9, which letter on the graph corresponds to the highest temperatures on the basis of this oxygen 18 to 16 data? And then question 10, which letter on the graph corresponds to a time when oceans were at their lowest levels? So if you put all that together using isotopes and tree rings and ice cores and cultural records and instruments and lake mud, all of that together has given geologists or earth scientists tools for being able to determine what the climate was like in the past. So what that data shows is that Earth naturally goes through cycles. Sometimes it's cold, sometimes it's warm. The cold periods we call glacial periods, the warm ones we call interglacials. So glacial periods last about 100,000 years, and then interglacial periods tend to be shorter, about a fifth of the time. So they last about 20,000 years or so. So throughout Earth's history, it's often more prevalent that we have colder periods in the blue down here than the warmer periods in the white. All right, so just for some comparison, so relative to today, if we had a glacial period in the past, it'd be 9 to 18 degrees Fahrenheit colder on average on Earth. And if an interglacial period, on average, it would have been about 18 to 30-ish degrees warmer relative to today. So when we talk about global climate change and human-induced climate change in modern times, I want to point out that it has been hotter on average in the past, and we know this from the types of data that we were just talking about. So if we look at climate fluctuations in the last 60 million years, so we kind of stretch out our time frame here, we can see that climate has gone up and down and up and down in terms of the average temperature that we have seen. And then just to give you a random statistic, but since about 3 billion years ago, there's been 6 ice ages that we know of in Earth's history. All right, so to finish up here, we're just going to talk about the natural causes of climate change. So our last lecture will be about human-induced climate change, but I want to set up the idea that climate can change naturally. So the graphs I just showed you, they showed that sometimes it's warmer and other times it's colder. So let's talk about how and why. So what geologists have noticed is that if you kind of line up where continents were in the past, there is a clear correlation between when continents were together, like in Pangaea, and then when an ice age occurred. So plate tectonics has something to do with it, that the distribution of the continents, if they are all together, something happens in terms of either atmospheric circulation or ocean circulation to create an ice age. So Pangaea, for example, was together 300 million years ago. There was an ice age during Pangaea. Before that, the other 2 major ice ages that we know about or are confident about also occurred when there was a precursor to Pangaea, when all those continents were together. So something about the distribution of the continents is a natural cause of climate change. A second, and very similarly related to the distribution of continents, is going to be ocean circulation. So if continents are arranged a certain way, then the ocean circulation and movement is dependent on the arrangement of continents. So if oceans are circulating a certain way, that affects the atmospheric circulation, it affects the distribution of temperature, distribution of heat around the globe. That's just to give an example, we have our present day Thermohaline circulation, so cold, salty water sinks, warm, fresh water rises, as we had talked about back in the ocean section. But in the past, during the Cretaceous period, there was this Tethys ocean, and the global circulation pattern, the global circulation pattern was different than it is today. The third and final natural cause of climate change, there actually is a fourth, which would be volcanoes, but a third cause of climate change is variations in Earth's orbit. These are called Milankovitch cycles, but basically it says that every 100,000 years, the eccentricity of Earth's orbit changes a little bit. So if we have a near circular orbit now on Earth, sometimes it becomes more eccentric or elliptical. That happens on a 100,000 year cycle. It kind of changes because sometimes then Earth would be slightly farther from the sun, and other times it's slightly closer. So that changes the amount of heat that reaches Earth's surface by about 20 to 30%. And then Earth's axis and the tilt of Earth's axis can wobble back and forth between about 22 to 25 degrees over a 41,000 year cycle. So if you are tilting the way that Earth is on its axis, you're changing again where the sun hits most directly on Earth's surface, which changes everything, basically in terms of heat, temperature, wind patterns, climate, weather patterns as well. So if we put all that together, this is just to show you the last 1,000 years of Earth's history, looking at all of those instruments. What we see is that the climate has stayed relatively stable until we hit about 1850. And then since then, records have shown that the Earth's climate is getting warmer on average globally with time. So our next and final lecture is going to be about climate change and human-induced climate change.